In the last two videos we looked at overwriting local variables on the stack using a buffer overflow. This time we're going to look at what is probably the most common beginner challenge when it comes to buffer overflows, which is a return to win challenge. And essentially we're going to try to overflow the buffer and redirect the execution to a function of our choice or to an address of our choice. And normally that function is called win or hacked or flag, and we'll just give you a flag or give you the shell, something like that. So we'll go through that, we'll do the usual basic file checks, we'll have a look at it in Ghidra and in GDB, PwnDbg, and we'll put together a couple of PwnTools scripts this time. So let's check it out. We'll start off with the basic file checks. In fact, as usual, we'll start off with compiling the binary even though it's already compiled. Just want to go through this just in case you're doing this on your local system. You need to be aware just to have these protections disabled. We can have a look at the file type of the file that we've compiled. It's obviously going to be 32-bit as we specified here. It's not stripped and it's dynamically linked. So I'll not go through what all that means again. Let's just have a look at the binary protections. And this will confirm that all of those protections are disabled. Great, alright, so let's have a look at the program, what happens when we run it. It asks us for a name, we can type in a name, and then it just says hi there. So we could try that again and enter in a longer command, longer value, and this time we get a segmentation fault. So we've crashed the program in some way. Maybe we overwrote an important variable on the stack, or maybe we actually overwrote the return address, which we'll go and have a look at shortly. Let's check out the actual source code of the binary. So if we have a look at our main function again, we've got this register name function which is called, and we can see that it has a 16-byte buffer. It asks for our name. It's going to use scanf this time instead of gets, and then it's just going to print out the response. So again, there's nothing to check to make sure this is going to fit in the buffer. And we've got this hacked function up here which is never actually called, so there's no logical way that the program should ever execute this hacked function. And our goal is going to be to try and call that function. So it might be called win in another challenge, it might be called flag. In this case it's called hacked. So as we mentioned in the first video where we kind of went through an introduction, whenever a function is called, you have the function, you have the parameters which are placed on the stack, and then you have the return address, and then the base pointer, and then the buffer, which is going to have all of our local variables and things that we're going to use in that function. So when we get to the end of the function, it's returning to the call-in function. So for example here we have this main function, it calls register name, it's going to set up this buffer, it's going to go through all of this code, and then it's going to return to main. But what if we overwrote the return address of main, which is on the stack, where it was supposed to return to, with another address? So we've seen that if we put in too many A's, we get a segmentation fault, and the reason is we're overwriting the return address with all A's, which isn't a valid memory address. So it tries to go there instead of going back to the main function, and then it realizes that's an illegal address, it doesn't exist as a memory address that can be executed, and it will cause the program to crash. In our case, instead of putting in those A's, we want to make sure that we put in the address of this hacked function. And we can get that in a variety of ways. So we'll have a look with Ghidra. We've had a look at Radare as well before, so you can do R2, return to win, AA, AFL. We'll see all of our functions here, and you have the address of the hacked function. One thing to mention is if we had compiled this with pi enabled, so remember we did the, where is it, no pi. If we did it with pi, we wouldn't actually see these addresses. In fact, let me just demonstrate that very quickly. Let's do it with pi, and let's check this again. AA, AFL. Notice this time we don't have those same memory addresses. What we have is offsets. So the offsets are the same. If we go and have a look, where was it hacked? It was this 9182. Where is hacked here? Okay, the offset's not quite the same, but the offset will be the same each time the program loads. The only difference is going to be this base address. So the base address is going to change each time, which means if pi was enabled, we wouldn't just be able to provide the hacked function address. We'd need to find out first of all what the base of the binary is, and then go from there. So I'll not confuse things too much. We have ways of doing that, and we'll get into it later in the series, but I just thought I'd quickly demonstrate that. We might as well kind of learn some things as we go. And now if we did checksec on that, checksec file Ret2Win, we'll see that we have this pi enabled. So it also affects setting up breakpoints and stuff in GDB, but yeah, I'll not get into that too much yet. Let's recompile it and say no pi Let's check the security again. That's it looking better. Okay, we could also use something like ObjDump, which I don't really use. ObjDump-D, Ret2Win, and we can go and get addresses from here as well. I don't typically use this. I normally get the addresses from either Ghidra or GDB. Let's also open up Ghidra then. So I'll do the Ghidra auto. Let's pass in the binary, and that's going to set that up for us. So we'll go over to our functions. We'll go over to the main function, register name, and again we could go and set up some of the variables here, say that's the buffer. And notice that if we would just go into the main and just go in through the functions here, we wouldn't actually see that hacked function. So it's important to go through the functions on the left as well and see if there's anything else of interest here. Normally in a CTF challenge it might be called hacked or win or flag, although I have seen it just being called an underscore, which can be a bit confusing. If you're looking through these, sometimes it can be something unsuspecting which has actually been introduced by the programmer or by the challenge creator. So we've got the hacked function anyway. We can go and click it here. We can see what the address of the hacked function is, and we can go and provide that then as the address that we want to redirect the execution to. So again, let's go back to the register name. So register name is called. The return address is going to be placed onto the stack so that it knows where to go back to once it's finished running this function. But if we overwrite that return address, instead of going back to that main function where it left off, it's going to go to wherever we tell it to. Let's go and have a look at this in GDB PwnDbg. We're going to exploit this manually, but I want to show also how we can find out what the offset of that return address is. So I'm going to load the file Ret2Win. Again, we can do our info functions, get all our addresses, and go and have a look through the code. This time what I'm going to do is I'm going to do a cyclic pattern, and I'm going to say a cyclic pattern of 100 bytes, and we get these characters where every 4 characters are different. So it's a way that we can actually go and search for the pattern and see what is the offset of the return address. So in other words, how many characters do we need to write before we're overwriting the return address? So if I now take a copy of this, run the program, paste that in, and it's crashed, which is what we'd expect it to, and what we're interested in is which 4 characters made it into the instruction pointer, because these are the 4 characters that we want to specify as being the hacked function, and in this case it was the ha. So we take a copy of that, we do cyclic-l to look that up, and we'll see that it's 28 bytes. So we need to do 28 A's, and then we need to put the address of that hacked function. And again, we can disassemble hacked and go and see what that address is. Take a copy of it here. In fact, what I'll do first of all, let's go and just visualize this a little bit better. So I'm going to do that Python2-C, and again we're going to print A's. This time we're going to do A times 28, because that was the amount of bytes we saw with the cyclic pattern. And then we're going to do some B's as well, just to go into the return address. So we'll do B times 4. And then I'm also going to do some C's just so we can see what happens with those as well. So let's do C times 32. We print those out, and this is what we're going to send to the program. So we'll go back, run it again, this time paste in those values, and we just want to make sure that the B's are what end up in the instruction pointer. So we can see that we've got A's filling up some of the registers here, we have B's in the EIP, and then whatever's left, the C's after that, are all on the stack. So we'll cover this later, but if you were doing a buffer overflow and there wasn't a hacked function, there wasn't an interesting function to jump to, what you might want to do is inject some of your own malicious code. So we could say these C's are malicious shellcode, and the B's, rather than pointing to the hacked function, will point to the beginning of this shellcode. So it'll jump there and then start executing. And we'll have a look at that shortly. We're also going to start having a look at the differences between 32-bit and 64-bit in terms of the registers and in terms of how the calling conventions work, because there are some differences, but there's not too many differences just yet, so we'll look at that more as we go. Okay, now we actually want to return to win then. We want to return to that hacked function, so I'm going to get this address again. I'm going to go back, and this time we'll do our A's. I'm not going to bother with those C's, but instead of the B's, we're going to put in this address. So I'm just going to paste this here just so I can type this out. We'll do \x 82. Remember, we're going in reverse order, but we're not reversing order. It's not 281, it's 8291 04 because we're reversing the order of the bytes, not the characters. So \x91, \x04, \x08. We will print this out. It's not recognizable characters, so we need to send this to a file. We'll call it Payload. And now, first of all, let's just, before we even go to GDB, let me just run the program. What was it called? Ret2Win. Send in that payload. And look what happened. We get this function is top secret. How did you get in here? We got a segmentation fault after that, because if we have a look at our code, think about it, this function was never supposed to be called. It doesn't even have a return in it. If we were in an actual buffer overflow, if we were doing this against a web server or something like that, we might need to be careful to exit safely or to redirect the execution. After we've called the hacked function, we might want to redirect the execution somewhere else to prevent the program from crashing. Let's go over to GDB. Let's do the same thing. Run, payload. We run it and we got the same thing. So it's showing the segmentation fault, which is why we've got this stack and registers being displayed, but we got through to the top secret function. What we'll do actually as well, let's disassemble that, what was it called, the function? I thought it was called do input, register name it was called, okay. Let's disassemble register name. This is where it's returning, so let's set up a breakpoint there. Let's break star address. I'm going to just do a normal run this time, so we run it, and okay, it seems to have saved what we did last time. Let me do this again. GDB PwnDbg. We'll select our file as Ret2Win, and then we'll set that breakpoint up. We'll run the program. It asks us for a name this time. Just put in crypto, and we're going to hit this breakpoint. And you see, whenever it gets to that return statement, it's saying let's return to register name let's return to main plus 21. So we could go and disassemble that and see exactly where that is, but you can see it down here as well. That's where it's going to go to. Now if we, let me hit continue, let's do that again, and this time send in that payload. We hit that breakpoint and notice what's different. Instead of the return to main plus 21 or whatever it was, it's returning to the hacked function. And you can see that we have the hacked function here instead of the code that we had last time. So we could step through it with next, or we can just hit continue, and we get the secret function's been executed. Okay, so let's also have a look at some PwnTools scripts. I've got the exploit.py put together here, and this is our first look at this template. So whenever you see this template, all this stuff at the top pretty much doesn't need to be changed. The only thing you need to change here is the binary name, so I've set that to return to win. This function is just to make it very easy to swap between debugging with GDB, running against a remote server, and running locally. So typically you might have a buffer overflow where you have the local binary, but you need to exploit a remote server which is running the same binary. And it can be quite annoying just going and having to comment out process and swap it to remote with the server address and port number every time, because sometimes you might be running against a local binary and then against a remote and then a second later against a local, etc. So this will make it very easy, whereby if we're running the program we can do Python exploit, and that will just run against the local binary. But if we do remote and type in an IP address and a port number, it'll run it remotely. And then we don't need to change anything, we can just go back to running it locally. Or we can use GDB, and that'll open up GDB PwnDbg automatically. You can see actually we've got the script here. This should have init PwnDbg in it, and this will only fire off if we use that GDB keyword in the command line. And then we can put other things here. We can say we want to break at main. We can put in any command that you would also put into GDB. Okay, apart from that, what else have we got here? We've got the debug set, so that was what we looked at previously. We can swap this depending how much output we want. And we have the context.binary set. So remember I mentioned last time, you don't have to specify, whenever you're packing addresses, you don't have to specify P32 or P64. You can just set the context binary, and then it'll look at the binary and see, okay, it's 32-bit, it's little endian, so from now on we'll assume that that's what we need to use, and that means we can just use pack. And it means that if you're swapping between a 32-bit and a 64-bit binary, which we will be doing, then you won't actually need to change the code at all. So I just thought I'd explain that stuff. I'll keep explaining this in other videos just so that anybody who's not catching the whole series will know what's going on, because I know a lot of people see this script and think, why is there so much code to do such a basic buffer overflow. Well, don't worry about it, this code always stays the same, you don't need to touch most of it. The important stuff is down here with the exploit. So we start the program, we've set our padding here, so we've said how many bytes we need to overwrite. In fact, I think in this case it was 28 bytes, wasn't it? Let's change that to 28. And the same here. I might have made some changes to the binary, I can't quite remember. And then we've also specified the hacked function, which again, the hacked function is different as well. So we can specify the address here, we could go and take that from Ghidra. Let's do that as well. So I'll comment this out for now, and we'll say 0x. That's the hacked function. And even if this was a 64-bit binary, it should be something like this, but we wouldn't need to specify those zeros because it would know what the architecture is from this context being set. And the flat is basically going to flatten down all these strings and integers and stuff into, where does it say here? It takes an arbitrary number of arbitrarily nested lists, tuples and dictionaries. It will then find every string and number inside those and flatten them out. So that's basically going to pack it all for us, pack our payload. We're going to write the payload to a file so we can use it again later. And then we're just going to send off the payload and get an interactive shell so we can see what comes back. You could also do io.receive lines here, but io.interactive will basically give you an interactive prompt where you'll get everything, and you'll be able to type more stuff if there's more stuff there. Okay, so let's try that again. Or not again, let's try it for the first time. Python exploit, we get top secret function, how did you get in here? And we can see the data that was actually sent off. Sorry, this is the data that was received. This was the data we sent off, was all our A's and then the address that we're jumping to. Remember, it's in reverse order, so 08049182, and that is what we can see down here as well. So if you compile the binary yourself, you may need to change some of these addresses around and change some of the padding. But these scripts are all going to be on the GitHub anyway. The binaries will be on the GitHub, and the code as well, so that you can compile it yourself. Okay, let's also have a look at this other script, which I put here called Ropstar. And this is basically going to automate that process a little bit more. So I've added some code. Again, we don't need to look at what's at the top, but I've added some code here to do what we did in GDB PwnDbg, where we use the cyclic pattern to try and find out how many bytes. And essentially what we're doing here is we're launching the program, and we're going to wait for the program to crash, and then we're going to read the core dump that it creates, and we're going to look in the core dump and see what was in the instruction pointer at the time of crashing, and then we'll have a look and see what the offset of that is in this cyclic pattern. Don't worry about it too much. This is just basically doing what we did in Ghidra to find out that the correct value should be 28. Down here we've used a ROP object, so we've created a ROP object from our elf binary, and rather than in our last example we had to specify the function, we can also specify the function like this. Because we've got the binary here, it knows where this function is, it knows where the hacked function is, it can find the address for us. This is doing the same thing, but we've created a ROP object and we're literally just calling the function. You can see that I've done print rop.dump here just to print out what this is putting together for us. We convert it into a ROP chain to get the raw bytes, and then again we just send this off at the offset. So we're just automating the process a bit. We're automating finding the offset to the instruction pointer. We're automating doing our ROP, so our Ret2Win, returning to this function, and then we're doing the same stuff here. We write to a payload, we start the program again because we crashed it earlier, and we send off the payload. So let's just try that as well. Is read only. Okay, overwrite. So I'm going to run Python Ropstar. It runs through, and we've got plenty of output. Most of this output, as you see, it's looking for the core file, and it finds that the instruction pointer offset was 28, which we knew anyway, but it's done it for us. And then the ROP gadget as well, so you can see it's found the address of the hacked function, and it's compiled that payload automatically. And again, we get our flag down here. That's about it for this video. So we looked at how we can actually exploit a buffer overflow to redirect the execution of the program to a function of our choice. We did that manually. We did it with GDB PwnDbg, we did it with PwnTools using a couple of different scripts. And there's a lot of different ways to do this. I'll just try and show as many techniques as I can as we go. In the next video we're going to look at something very similar. So we're going to look at a Ret2Win style challenge, but the difference is the function will require parameters. So in this case we've got this hacked function. In the next one, it's going to take in a couple of parameters, and it's going to check to make sure those parameters are equal to what it's expecting. So we'll look at how to supply those, and that'll be the first time that we'll look at how 32-bit and 64-bit binaries deal with these things differently. So yeah, I hope you've enjoyed this video anyway. Any questions or comments, leave them down below. Thanks.